Okay, hi everybody. In this lecture, we're going to talk about special second order equations. So a general second order equation can be written in the form y double prime is a function of x, y, and y prime. Okay, if it can be solved explicitly for the second derivative. Okay, and we only know how to solve first order equations so far. So if we're going to know how to solve what I'm going to talk about, they better be very special equations because they have to reduce to first order. But there are three cases that it turns out that you actually can do by first order methods. So case one would be when you have a function of the form of the ordinary differential equation of the form y double prime is a function of x and y prime. In other words, y is missing. Okay, so when y is missing, that means we can do a trick. And here's the trick. The trick is to let v be y prime. Then v prime is y double prime. And then the equation becomes instead of y double prime, we have v prime is equal to f of x and v. And this is a first order equation in v, solved by the methods that we learned in this chapter. So we solve for v, and then v is y prime, and so y of x is the integral of v of x dx, because v is y prime. So that's just the fundamental theorem of calculus. So that's the fundamental theorem of calculus, tells you that's true. Okay, so that kind of problem is really easy. Okay, and falls under, it's a second order problem, but it falls under the blanket of what we already know. So for example, suppose I give you the equation y double prime plus ty prime squared equals 0. Okay, and I ask you to solve that. That's a squared. That's a 2. Okay, so you notice there's no y. So you let v equal y prime. So v prime is y double prime. And so the equation is v prime plus tv squared equals 0. That's a separable equation, right? Because we can write this as dv dt. And this is equal to minus tv squared. So that says dv over v squared is equal to minus t dt. So now my equation is separated. I can integrate on both sides. This is v to the minus 2. It integrates to minus v to the minus 1. This is minus t. It integrates to minus t squared over 2 plus c. Okay. So I have multiplying through by minus 1. I have 1 over v is t squared over 2 minus c, but that's just another constant. So let me just call it plus c. Okay. So this is, since I'd like to take a reciprocal to solve for v, let me just say this is t squared plus, you would do 2c, but 2c is an arbitrary constant. So I can just write it like this. Remember, this c is not the same as that c, but it's just an arbitrary constant, so it doesn't matter. And now I can take reciprocals, And so I get v is 2 over t squared plus c. All right, so now we've solved for v, but v is y prime. So this says y prime, well, let me write it as dy dt is equal to 2 over t squared plus c. So that's a separable equation again. I get dy on the left. I get 2 over t squared plus c dt on the right. I integrate on both sides. On the left, I'll get y. On the right, now this is one of those integrals you have to remember. What do you get? You get 2 times the arctangent of t over square root of c. So, which is again, just another constant. But since we have another integral, you get a second constant. So let me call that C2. Thinking that the first one is C1, okay? And sorry, this should be a 2 over C. Okay, now let me remind you, this is one of the integrals you should remember, but let me just remind you, just in case you don't. The one I generally remember and that you always sort of have to remember is that dt over t squared plus 1 is arctangent t. Okay, so now I'm just going over the calculus 2 for you. But this one isn't t squared plus 1, it's t squared plus c. The 2 is irrelevant, right? We can move the 2 outside of the integral. So what if you have the integral of dt over t squared, let me say, plus a squared? So I don't have to write a square root. Instead of writing c, I'll write a squared, okay? And then I want to integrate that with respect to t. So how do I use this one to solve for that? You make a simple substitution. You let c be, well, no, sorry, not c. Let s be at. Then ds is a dt. And t squared plus a squared is equal to, I'm sorry, this should be s, oh, this should be as is equal to t. Whoops. Okay, so then t squared plus a squared, so the s should be on the other side, my bad. And so this becomes a squared s squared plus a squared, which is a squared times s squared plus 1. Okay. All right, and how does that help us? Because now when I go to rewrite this integral, for dt, I put in a ds. For t squared plus a squared, I put in a squared times s squared plus 1. Okay, so now the a and the a squared, they can come outside. That becomes a 1 over a. Then I have the integral of ds over s squared plus 1, which is 1 over a arctangent s. But s was t over a. Okay. So that's how that's reminding you of the substitution, the Calc 2 substitution. And you see, that's exactly what we got up here, except a squared is replaced by c. And so a squared is replaced by c. And so this should be a square root of c, actually, down there. Okay. From this calculation, you end up with a square root of t over a. Okay. Okay. All right, so that's an example and the first kind of special case of differential equation. The second kind of special case what we'll call case 2, is where you have the x variable missing. So y double prime is equal to f of, I'm going to switch pens here because this one's not writing so well. It's almost out of ink. Y prime is f of y and y prime. I'm sorry, I said y prime. Y double prime is f of y and y prime. Okay, so what's the trick? So yeah, let me emphasize that x is missing. Your independent variable is missing. Okay, so that's the deal. The independent variable is missing. So how do we deal with that? The trick is to let v be dy dt. And why does that help? Well, now dv dt is the second derivative, or y double prime, of course. So that says that dv dt is f of y and v. Okay. So you look at that and you go, wait a minute, that doesn't look much better than before. Because I still have a t, y, and a v. That's too many variables. It's a first order equation, but it's not a good kind to solve. But actually, we've used a trick like this before, because now what you say is, wait a minute though, by the chain rule, dv dt is equal to dv dy times dy dt, which is dv dy, but dy dt is v. So dv dt can be written as v dv dy. Okay, we saw that before in our escape velocity. So this is v dv dy is equal to f of y and v. Okay, and so now you have a first order equation where y is acting like the independent variable and v is acting like the dependent variable. Okay, and hopefully you can solve. But at least you've got it to a candidate for something you have the tools to solve. Okay, so let's do an example of this. So here is an equation. Suppose you have y double prime plus y prime squared is equal to 0. Okay. So you look at this equation when you're coming along in a test and you say, wow, okay, second order, I don't know too much about second order, and especially nonlinear ones, but it's y double prime, and y prime, but there's no x. So x is missing. Okay, so let's go ahead and see if we can make this trick work where we let v be y prime. So v prime is y double prime. But more importantly, v prime is dv dt, which remember, let me go over the chain rule again to remind you, that's dv dy dt. So that is v dv dy. Okay, so here I have a y. Now the equation says, rewriting the equation now, we have y times y double prime, which is v prime, but v prime is v dv dy. So there's my y double prime in parentheses, plus y prime squared, which is v squared, is equal to 0. Okay, so that says v y dv dy is equal to minus v squared. So that's another separable equation. So we can write this as dv, and now the v squared comes to this side, so this will be dv over v is equal to minus 1 over y dy. Okay. dy comes over here, the y comes over here, I'm leaving the negative. So I can integrate on both sides. Then I get ln v is minus ln y. Okay. So that says that v, now take exponentials on both sides. Well, be a little careful because you can't exponentiate with this in this form because you'll run into trouble with, you have to have a logarithm on the outside by itself. So this is the log of 1 over y plus c. And now you can exponentiate. So when you exponentiate on this side, you'll get back v. Over here, I'll get back e to the ln 1 over y, which will give me 1 over y, times e to the c, which will just give me another constant. Okay. So I get v is c over y. I'm not done because I wasn't asked for what v is. I need to know what y is. But now I use the fact that v is dy dt, or dy dx rather, in this one. So this is equal to c over y. So I can, again, rewrite this equation. So I get y dy is equal to c dx. Okay. And now I can integrate on both sides because that's separable. Separated, I should say. So I get y squared over 2 is equal to c1, let's call it c1x, and then I get another constant of integration from doing this integral. Here's the c1, it gets multiplied times x from the integration, then you get another arbitrary constant. And that's what you expect because you started with a second order equation. You expect and you need 2 arbitrary constants. So we got that in the first one and we see it again here. You better. It's a second order equation. You're going to need 2 arbitrary constants. Okay, and the last thing I want to talk about, the last trick in this is if the other variable is missing. So the last case is almost too easy to mention and be a separate case, but let's go ahead and mention it anyway. Suppose you have an equation where both x and y prime are missing. So you have y double prime is a function of, sorry, I just said it and then didn't write it, is y double prime is a function of y only. So in other words, x and y prime are missing. Then what works? What works is basically the same substitution that we just used when x was missing alone. So when x alone was missing, what we did was we said let v be dy dx. Okay. And then y double prime, so that's y prime, and y double prime then is d prime, or dv dx. Reviewing your calculus 1 with you. Okay. And so the equation then becomes v prime is equal to f of y. Well, that doesn't look so great because this v is dv dx, and now you have v, x, and y not in a good situation. You just need 2 of them. So how did we resolve it in case 2? What we did was we used the chain rule. So dv dx is dv dy times dy dx. And dy dx is exactly v. So this becomes v dv dy. And so our equation up at the top here, the second derivative is dv dx, y double prime is v prime, which is dv dx, which we have now written as v dv dy. So there's my y double prime. Took a long way to say that. And it's equal to a function of y. And now that's a first order equation involving only y and v. And so you hopefully can solve. It's first order. And you hopefully can solve via the methods we know, okay, that we learned already in this chapter. So let's do one final example of that. Okay, suppose I give you the problem that y double prime is ln of y cubed. Okay, so that's something of this form because it's a second derivative and it's a function of y only, no x, no y prime. Okay, so I'm going to let v be dy dx. Then dv dx is y double prime. On the other hand, dv dx is also dv dy times dy dx. So this is v dv dy. And it's maybe good to write it out every time so you can get used to it. So now we go to our equation. And for y double prime, I write v dv dy. And that's going to be equal to ln of y cubed. Okay. So that's a separable equation, but I do want to remind you, maybe that was off the thing. So the equation becomes v dv dy is ln of y cubed. So it's a separable equation, but I do want to remind you how to integrate those things. So our equation said v dv dy is ln of y cubed. So this becomes v dv is ln y cubed dy. Okay, that's not great to integrate it that way, but it is separated, so we can integrate on both sides. But this one is going to give you trouble unless you use some properties of logarithms. So this is also the same as 3 times the integral of ln of y dy. Okay, v dv, I'd be willing to bet almost everybody in this class can integrate that. Okay, so you can get b squared over 2. If not, you're in trouble. But how do you integrate ln y? Well, I'm going to hesitate for a second and let you think for a minute. But it's not the integral, it's not 1 over y. That's not, that the rule goes the other way. So how do you integrate this? It's integration by parts. So the integral, let's come over here. So the integral of ln y dy, you have to integrate by parts. So you let u be, oh, maybe u and v aren't the best letters. How about s and t? Let me let s be ln y, then ds will be 1 over y dy. Okay. Then dt has to be the rest of the stuff in the integral, which is just dy. So when you integrate dt, you get t is equal to y. Okay, and the integration by parts formula, which I hope that you have memorized, says the integral of s dt is st minus the integral of t ds. Okay, so now that's the integration by parts formula right there. So that's what you should remember from calculus 2. It's right at the borderline between 1 and 2. Hopefully you did it in both. So here's our integral. And by this formula, it's going to be s times t, so that's y ln y, minus the integral of t ds, which is y times 1 over y dy, which is just dy. So this integral that we're looking for is y ln y minus y plus c. And you can check. If you differentiate this, you will get ln y. That's fundamental theorem of calculus. If you integrated, took an indefinite integral, what you get on the other side, if you differentiate that, you better get back to the integrand. Okay, so this integral that we're looking for here, just the integral part, is y ln y minus y, and there's a 3 there. So this is 3 y ln y minus 3y plus c. Let's call that C1. Okay. So that says that v squared is equal to 6y ln y minus 6y plus another constant, 6 times the constant, so that's still a constant. Okay. And now finally, we still have to solve for y, so I better go ahead and take a square root. So this is, so v is, so v is the square root of 6y ln y minus 6y plus c1. And this is dy dx. And so dy dx is equal to this. Okay. Now in principle, we can separate this. And it looks good so far. So you can integrate on both sides because there's no x over here. This right-hand side, you can integrate. You get x plus c2. But on this side, you're in trouble because oh, I'm sorry, I had it where you couldn't see. So I just separated the variables and integrated. The right-hand side, obviously, you can integrate. But in this left-hand side, you're in trouble. You can't integrate that. So sometimes all you can do is say there exists a solution. And if you wanted to solve this more explicitly, the best you can do is do numerical approximations if you had conditions that you knew y had to satisfy so that you could get a C1 and a C2. But in general, that's not an integral that can be solved. Okay, so you can't write down an exact answer for that one. But anyway, hopefully you see the idea, you see some of the problems that you can run into. And okay, that's it for this lecture.